In part 2 of module 5, we're going to be talking about refrigerators and heat pumps after having talked about heat engines in part 1 of module 5. So refrigerators and heat pumps are another type of device that is similar to a heat engine but has a different purpose. And the purpose is that they are special devices to transfer heat from low temperature to high temperature. Okay, so they're special devices to transfer heat from low temperature to high temperature. And this is how essentially a refrigerator works. It takes heat from a low temperature environment, which would be the inside of your refrigerator, and moves it to the outside or to your room where your refrigerator is in. Okay, so sometimes people think of refrigerators, yeah, they just get cold by having cold air go inside. But actually, what's happening is we actually take out heat from the inside of the refrigerator and exhaust it to the outside. And it's also exactly the same way that a heat pump works or a heater works. A heater takes cold air and makes it warmer. Okay, so they work in the same way. The only difference between a heat pump and refrigerator is its goal. So let's look at a refrigerator first. And a refrigerator diagram would look something like this. So we'll do a simplified diagram and then we'll look at the complex diagram. So the simplified diagram looks like this, and I'm going to call this fridge. Okay, not just refrigerator, but I'll just call it fridge. And if we have our fridge, essentially what we're doing is we're taking heat from a cold place, okay, or from a cold reservoir at temperature L, and we're moving it to a warm reservoir with temperature H. This is QH. And we do this by putting some work net in. Okay, so our work is in now, it's not out. And so what ends up happening is we're essentially cooling down this bottom part here. We're cooling down this temperature L. So TL is actually, this part is actually our refrigerated space. So the mechanism for the fridge works outside of the refrigerated space and allows us to take heat out of that refrigerated space, making it colder in temperature, keeping our temperature TL low. Okay, then it goes through the fridge system, which we're going to zoom into in a second, and releases some hot air to the environment. So that would be, for example, your kitchen air. Okay, so the top part would be the warm part, and this would be your kitchen air essentially. So what a fridge actually does, it takes heat out of the fridge space and makes your kitchen air warmer. So essentially your fridge is actually the same thing as a heater for your kitchen. Okay, the fridge actually acts as a heater for your kitchen. Okay, so you can see how a fridge could be used as a heater as well. Obviously, that's not the goal of it, but it could be possible. And refrigerators usually use R134A as their fluid, or it's also called refrigerant. Okay, and that's why we have tables for R134A. Now, if we zoom into this system here, if we look at this system here, and we look at a control volume of this system, we would have the following system. We essentially would have the opposite of what a heat engine would look like. We essentially have an evaporator here at the bottom, and this evaporator sends sends R134A, sorry, into a compressor, Okay, and this compressor then compresses the air through work net coming into the system. Okay, so our work net is inside into the system. And this R134A is now compressed, goes through a condenser. Okay, so it exchanges heat with TH. Okay, so it exchanges heat with our kitchen air essentially with TH. Okay, then going through the condenser, it then goes through a valve. Okay, so this is a valve. And the process starts again going through the evaporator. Okay, so that's essentially the process used in a refrigeration cycle or in a heat pump cycle as well. So in a heater cycle as well. So here we have our TL, which is our refrigerated space. Okay, and essentially we have QH being exchanged here, QL at the bottom, and that's our system drawn in a more complex manner. And our control volume would essentially be drawn all around here, separating our fridge system from our TL, TH, and our work coming in or out. So if we look at the top diagram, if we look at that, we can actually do the sum of the energy in is equal to the sum of the energy out. And if you look at energy in is equal to energy out, we now have that QL plus work net coming in is equal to QH. And so you come out with the equation that work net is equal to QH minus QL, which is actually the same equation as for the heat engine. So that's going to be very useful because we always have the same equation to find work net from QH and QL. Everything is reversed, so it's essentially exactly the same thing. Okay, now for a refrigerator, we don't use thermal efficiency to measure performance. We use another coefficient, and this is called the coefficient of performance. So in heat engines, we use thermal efficiency. Here we can't use thermal efficiency because our goal is not to create work, it's to create something else. So the COP, or coefficient of performance, which is also sometimes called beta, okay, so it's either beta or coefficient of or COP, is equal to the energy sought over the energy that costs. So it's essentially the energy we want, the desired output over the required input. So if we extend this line, we have at the top, we have desired output divided by required input. Okay, and so that's how we would solve for our refrigerator. So in the case of a refrigerator, we would call it COP of refrigerator, or little r, or we would call it beta of little of r. And what is the energy sought in a refrigerator? What is it that we're trying to increase in a refrigerator? Well, in a refrigerator, we're trying to keep TL cold. We're trying to keep the temperature low. So how do we do that? If we increase the QL, that means we're going to keep our TL very low. So our energy sought in a refrigerator is QL. We want QL to be high. If QL is high, that means we have a higher coefficient of performance. And we're going to divide it by the energy that costs. So in a refrigerator system, the energy that costs is essentially the other energy in. And the energy in is the work net. So the work net is the energy used to keep essentially our QL high and our TL at a low value, our temperature at a low value. So we can rewrite this as, from our equation for W net, we can also rewrite this as QL over QH minus QL. And we can rewrite this in another manner by saying that it's 1 over QH divided by QL minus 1. Just different ways of writing the same equation. Okay, so now let's look at heat pumps. Heat pumps are slightly different because heat pumps have for goal to heat up the room or to heat up an environment. That's the goal of a heat pump. Now, a heat pump has exactly the same cycle as a refrigerator, as we've said before. And this same cycle is used to maintain a heated space at high temperature. So we're trying to maintain a heated space at high temperature. So if we draw a diagram of our heat pump, we just have our heat pump, which we're going to call HP. Okay, do not confuse heat pump and heat engine. They are different. And so we have QL coming in from a temperature L. We have QH coming out to a TH. And our goal is to keep the TH high, and our work net is in again. So with work, we're able to keep our QH high. So once again, our work net is equal to QH minus QL. It's exactly the same system as a refrigerator. And the beta of the heat pump, or the COP of the heat pump, you'll see it written in both ways, is now equal to the, again, energy sought over the energy used. And the energy sought now is QH. We want to keep QH high over the work net. And we can rewrite this equation in the same way as before as QH over QH minus QL. And this is also equal to 1 over 1 minus QL over QH. Okay? So the best way to understand these types of problems is to do some example problems. And we're going to do two very simple examples of a heat engine at first, and then looking at a different system, which we'll have to determine if it's a refrigerator, a heat pump, or a heat engine. Okay? So let's do these two examples to try and understand what's happening and how we can apply them to practical problems. Okay, so let me copy over the diagram. So we have a question that says a steam power plant with a power output of 150 megawatts consumes coal at a rate of 60 tons per hour. If the heating value of the coal is 30,000 kilojoules per kilogram, determine the overall efficiency of this plant. Okay, so first step is to figure out what type of system we're dealing with. So we know that we're given, we know that we're given that it could either be a heat engine or a heat pump or a refrigerator. I'll say R for refrigerator. Now, in our case, we have a steam power plant. And if we looked at earlier, we know that a steam power plant is there to create some work. It's creating power. So that means it's going to be a heat engine. So we're going to assume that it's a heat engine. And I mean, we don't even have to assume it. We know that if something has a power output, it can only be a heat engine. So the second step in our problem is to draw a diagram. So I always like to draw the diagram, the simplified diagram of every step, just to write what information we have and how we can deal with this information. Okay, so we have our diagram. So our diagram is going to have, at the top, is going to have a furnace. Okay, our power plant has a furnace at the top, or our TH space, okay, our T hot space. And our T hot space is going to have a Q dot H coming into our heat engine, which has the 4 different elements to it. We know that the heat engine is going to output some power net, or some work net if you want to keep it in work form. Here we're going to use power because we're given power output, so we're going to use everything in terms of time, so W dot. And then we also know that Q dot L is coming out and is going to some sort of sink, usually a river or something. Okay, so that's our diagram. So second step is to draw diagram. Now the third step in our problem is so I'll write it here on the left. Third step is to write out all information on diagram. So we're going to write out all the information on the diagram that we're given in the problem. So we're told that a steam power plant produces 150 megawatts of power output. So we know that work.net is equal to 150 megawatts. Okay, we can change the units later, but let's just write megawatts, okay? And we're told that it consumes coal at a rate of 60 tons per hour. So we're told that in our furnace, essentially, we have 60,000 kilograms, or 60 tons, consumed per hour. Okay, and we're also told that the heating value of coal, so the heating value of coal is equal to 30,000 kilojoules per kilogram. So that means that for every kilogram of coal you burn, you're going to get some heat of 30,000 kilojoules, okay, into your system, into your heat engine. So from that, you can actually determine your Q dot H. Okay, so we'll look at that in a second. So do we have any other information? No, we're not given any other information. The last information we're given is that we're trying to find, so it's just determine the overall efficiency of the plant. So since we're trying to determine the efficiency of a heat engine, we're going to use thermal efficiency. So our goal is to find N thermal is equal to work dot net divided by Q dot in. Okay, and from this, we can now go through. So we know that Q dot in the case of a heat engine, is equivalent to Q dot H. So we have to find work dot net, which we already have, divided by Q dot H. So the next step is to find Q dot H. So Q dot H, given the information in the problem, is just equal to the mass flow rate, okay, of coal through the system multiplied by the heating value. So it's the mass flow rate of burning multiplied by the heating value. Okay, that's how you know how much energy is coming out of the furnace, assuming all the energy goes directly to our heat engine, directly to the top of our heat engine. So we have that this is equal to 60,000 kilograms per hour multiplied by 30,000 kilojoules per kilogram. And we have an answer for this that says that we have 1.8 times 10 to the 9, and if we work out our units, we have kilojoules per hour, because the kilograms cancels. And since we have kilojoules per hour, we actually want to change that value to kilojoules per second so that we have kilowatts. So we want to change our value to kilojoules per second or kilowatts. So doing this, you have to divide by 3,600, okay, to get it per unit per second, sorry. And so you get that you have actually 500,000 kilowatts of energy going through Q dot H. Okay, so the energy coming in is just the mass of the coal per hour being burned multiplied by the kilojoules you get per kilogram being burned. Okay, hopefully that makes sense. And so we can write that our thermal efficiency is just equal to 150,000 kilowatts, which is 150 megawatts, over 500,000 of energy in. So we get an efficiency of 30%. So you can see how from finding Q dot H, we actually have a thermal efficiency of 30% for our plant. We haven't gotten 100% of the energy from the heat coming in directly to the work dot net. The other energy is going to Q dot L. So you could find Q dot L from that stuff. It's not asked in the question, but you could say, I know that work dot net is equal to Q dot H minus Q dot L. So I could find Q dot L and figure out how much energy has gone to the sink, essentially, or to our river, for example. So you would have Q dot L is equal to Q dot H minus work dot net, whatever's left over, essentially. So for this, you would have 350,000 kilowatts. Okay, that's just an extra information on the problem. Now, the next thing I want to do is another type of problem that's a little bit more complex than this first one, and it's this second problem right here. And we are given some interesting information, so it should help us in determining what type of system we have. But let me copy over the problem, and then we'll get started on it. So we are told that when a man returns to his well-sealed house on a summer day, so we have the information that the house is well sealed, okay? So that's going to give us an information that we probably know that the house is not losing any heat to the outside, so it's insulated. So we can say that this is equivalent to saying insulated, okay, for the purposes of our problem. He finds that the house is at 35 degrees Celsius. He turns on the air conditioner, which cools the entire house to 20 degrees in 30 minutes. So we're told that it cools a house in 30 minutes to 20 degrees. If the COP of the air conditioning system is 2.8, determine the power drawn by the air conditioner. Assume the entire mass within the house is approximately equivalent to 800 kilograms of air, for which CV is 0.72 and CP is 1 kilojoules per kilogram degrees Celsius or degrees Kelvin. Okay, so kind of a complicated problem that we don't really know how to approach at first look because we're given a lot of information. The first thing we have to figure out is, are we dealing with a heat engine, a refrigerator, or a heat pump? Well, since we have an AC system, our goal for an AC system is to keep our air cool. So we want to try and keep our air cool. In order to cool the air in the house, what we have to do is we have to use some sort of refrigeration system. Okay? What we're going to do is we're going to take energy out from the house and we're going to run it through an AC system, and this AC system is going to exhaust some hot air outside. Okay, so it allows us to have a system that is actually going to keep the air cool in the house by extracting energy from inside the house. Okay, so we can assume that it's a refrigerator. Okay, so an AC can be thought of as a refrigerator. Okay, a heater would work in exactly the opposite way. You would have the exact same system, but now you're trying to heat the house, so the heat would go into the house and it would take some cold air from the outside to heat through work. Okay, so we have the system, and the first thing we can draw is once again our little diagram for our refrigeration system, which is going to look like this. So we have our refrigerator, and our refrigerator is going to have Q dot H going up into our TH, which in our case is going to be the outdoors or the outside. And this refrigerator is taking some heat out of the house. And so this bottom part at TL is going to be the house. And in order to take some heat out of the house, which is already colder than outside, we're going to have to do some power or some work net. Okay, so we know it's a refrigerator. The other information we're given is that the change in temperature of the house is 35 minus 20, which is equal to 15 degrees Celsius. And the change in temperature is also equal to 15 Kelvin. Okay, so you could have converted everything to Kelvin, but it's equal to a change in 15 Kelvin or 15 degrees Celsius. And we're told that this happens during a change in time of 30 minutes. Okay, I'm just writing down the information that we're given. We're also told that the COP of the refrigerator is equal to 2.8. So we're told that COP is equal to 2.8. And the question asks to determine the power drawn by the air conditioner. So what we're looking for is this term right here. Okay, we're looking for W dot net. Okay, so let's write down some equations that we have for W dot net. So in order to find W dot net, we can write down some equations to figure out what we have. So W dot net, we know, is equal to Q dot H minus Q dot L. Okay, that's our equation. Now, do we know any information on Q dot L or Q dot H? We have to figure those out. So we don't know Q dot H, we don't know this, and we don't know Q dot L. So we're going to have to figure them out. Now, there's another equation that relates work dot net with Q dot L as well. There's another equation that says that the COP of R, not the COR, but the COP of R is equal to Q dot L over work dot net. This equation is probably going to be better. This equation here is going to be nicer for us because we already know one term. So we already know COP of R. So the only thing we have to figure out is our Q dot L. If we can find our Q dot L, we can find our work dot net. So let's define what Q dot L is, and let's try and find out what it is. So we have Q dot L is equal, if we talk about it in terms of the actual thing that Q dot L is it's the heat removed from the house okay, heat removed from the house divided by the time. Okay, the Q dot means that it's divided by the time. Okay, so that means that we have essentially Q dot L is equal to QL, which is the heat removed, divided by the change in time. So we already know the change in time. The change in time is 30 minutes. Okay, so we know that. And we can convert that to seconds by multiplying by 60. And now we just need to find our Q in. Okay, or our, sorry, not our Q in, but our QL. So let's do a first law analysis on the house. We know the house has a control mass, okay? Our house is essentially a box with 800 kilograms of air inside the box. Okay, we have 800 kilograms of air inside the box. And we know that we have some QL leaving. Okay, we know that QL is leaving. Now, by convention, whenever we do the first law on a control mass, so if we do the first law on control mass, we say that Q dot in, or Q in, sorry, minus work out is equal to mass times delta U. Okay, and that's little u, so I'll actually leave it in most normal form at the start. So delta U plus delta KE plus delta PE. And delta K and delta P go to 0 because we're not given any information on this. And so we can find what, and we also know that there's no work because there's no change in volume in the house. Okay, so work out is equal to 0. So we're left with the equation that says that Q in is equal to M times little u2 minus little u1, the change in internal energy between time 2 and time 1. And so that means that Q in is equal, for air, we're going to be using our CV or CP formula to figure out our change in U. Now, in a change in U, do we use CP or CV? So you should be able to answer that by yourself. So I'll let you answer that. Pause the video if you want to figure it out. But U2 minus U1, since we're focusing on a change in internal energy, will always be equal to mass times CV T2 minus T1. And so we're given CV in the question, we're given the mass in the question, and we're given the temperatures in the question. So we have that Q in is equal to 800 times 0.72 times 20 minus 35. Okay, T2 is 20 degrees, T1 is 35. So we're going to have a negative Q in. So Q in is equal to negative 8,640 kilojoules. So now that it's equal to negative 8,640 kilojoules, we can actually say that our QL is not in, it's out. So what we just found was that Q in is negative. Okay, we have a negative for Q in. Therefore, it means that Q out, which is equal to QL, is going to be a positive. It's going to be equal to 8,640 kilojoules. And now we can plug that in to our equation above to find Q dot L. So we can say that Q dot L is equal to 8,640 divided by 30 times 60 to get the units right. And we get that Q dot L is equal to 4.8 kilowatts. So based on that, we can find work dot net from our equation for coefficient of performance by rearranging it. We can say that work dot net is equal to Q dot L over COP of the refrigerator, which is equal to 4.8 over 2.8, which turns out to be 1.71 kilowatts. So by putting 1.71 kilowatts of work net, we're able to take out 4.8 kilowatts of energy from our fridge system. Okay, so that's going to be very important, and it's going to help us understand the problem. So recapping this problem, because it is a new type of problem. We first identified that we have a refrigerator system and that we're going to focus on finding work.net. We have two different equations to find work.net. We identify that the COP equation is better because COP is given to us. Then we have to find Q.L. In order to find Q.L, what we do is we now do a first law analysis around the house system. And we look at how much heat has left the house. And by doing a first law analysis on the house, we can figure out our Q.out, or our Q out, essentially. Once we find that out, we can plug that back into our COP equation and find our value for work.net within our other system, our bigger system of the refrigerator. Okay, so it's kind of a two-part problem where you use first your second law that we've derived, and then using your first law to adapt to do a certain part of the problem within the house in this case. Now, if you were given a different type of problem where you would have, so for example, instead of the house, you would now have a pipe with air flowing through the pipe, and the air flowing through the pipe goes from 35 to 20 degrees. Okay, and that's your system. Now you would use a control volume analysis because now you have some mass coming in and some mass coming out. And let's say that you have a refrigerator attached to this pipe. So you have a refrigeration system that takes Q.L out of the pipe, for example. Okay, so this is our refrigerating system. Goes to the outside with Q.H in TH sink, essentially, with some work.net. We now would have to analyze our problem in the same exact way. So let's take the previous problem as an example. Okay, this is 35 degrees Celsius, but now it's air flowing through a duct. Now it's not really a problem of time anymore. So what we have is we can use our first law for open systems that says that Q.in minus work.out is equal to delta H plus delta KE plus delta PE. And we could have kinetic energy and potential energy, but assuming we don't, we would be left with, in our system, we would be left with Q.in is equal to M dot times HE minus HI, H exit minus HI, so this would be E and I. And in this case, we would write M dot times CP times TE minus TI. So kind of the same problem, but now you would apply the first law to this system here, which would, in this case, be an open system because we have an open system. So you can see how you have to apply the first law to solve the problem. Okay, and some of your example problems will help you out with this endeavor. So this concludes part 2 of module 5. And moving forward, we're going to be looking at the Clausius statement and reversible and irreversible processes within this second law of thermodynamics to try and understand what our limits to performance are. So we'll see you for that in part 3.